Welcome to our paper, SCARP, 3D shape completion in arbitrary poses for improved grasping. 3D shape completion aims to recover the full 3D shape from a partial view of the object or scene. Motivation. Many robotic agents, such as a self-driving car or an autonomous drone, rely on a complete representation of the scene to perform tasks successfully. However, real-world observations are partial due to self-occlusion or insufficient number of camera views. Consider a robotic arm performing tabletop manipulation. It first captures the scene from multiple viewpoints. An incomplete point cloud would lead to grasp proposals being assigned incorrectly that would cause the manipulator to collide with the actual objects on the table. In this work, we consider the task of completing the shape of the partial point clouds in their arbitrary poses to improve the task of grasping. Now first, let's look at why shape completion hard. Existing shape completion methods incorporate a training scheme by learning a prior over multiple instances of a category and then using the learned space to infer on partial inputs. However, their underlying space lacks an understanding of the object's pose, as every object in every individual pose must be modeled as a separate point in the latent space, leading to poor generalizability. Thus, existing 3D shape completion methods expect the partial observations to be in a fixed canonical pose, limiting their use in the real world where the objects are found in arbitrary poses. Baseline system. Existing methods depend on an external canonicalization method to pre-process the partial input, resulting in error propagation and a suboptimal shape completion. Our baseline is a multi-stage pipeline that first uses Condor to canonicalize the partial inputs, completes the shape in the canonicalized form, and then transforms the object back to the original pose using Condor's predicted transform. Results on baseline models. As can be seen, the baseline models struggle to recover the detailed full shape in the correct pose. Now let's look at the architecture of the proposed approach, SCARP. SCARP learns a disentangled representation of pose and shape by getting trained on a multitask objective to perform canonicalization, shape completion, and 6D pose estimation in a single end-to-end network. We first extract global equivariant pose features using tensor field networks and geometric shape features using PointNet++. Our generator is trained to predict the completed shape in the canonical pose by taking a distance-aware chamfers distance with the canonical form of the ground truth. We learn pose estimation by supervising the predicted 3x3 rotation matrix using a combination of DCD and L2 losses with the ground truth in its original pose. More details about the architecture can be found in the paper. Now let's look at some results on SCARP. As can be seen, SCARP is able to recover the detailed full shape in the correct pose, whereas the baseline models struggle to do so in many cases. In this case, the pose of the output planes is flipped in the baseline models, whereas SCARP is able to get the correct pose. Our superior results are also evident from the quantitative metrics, where we outperform the best baseline model by 45% in the maximum mean discrepancy Earth movements distance metric and 34% in chamfers distance metrics. Let's look at some applications of SCARP in grasping. SCARP can be used to improve grasp pose estimation. Here we show an example of a real-world object captured from a single view. The grasps are predicted by a state-of-the-art grasp proposal network contact GraspNet. The green color indicate that these grasps do not collide with the observed object. However, when we transfer these same grasp poses to the actual object on the table, we see that they are inside the actual object as indicated by the red color of the grasps. As a result, the manipulator indicated by the gray fingers collides with the object as it tries to grab the object using one of these predicted grasp poses. We overcome this challenge using SCARP by completing the partial observations. As a consequence of the shape completed output, the grasps predicted on the observations do not collide with the actual object, thus improving the task of grasp pose estimation. We show additional results on real-world scans. As can be seen, SCARP does not need domain adaptation and can complete real-world objects in their arbitrary poses based on its priors learned on synthetic datasets like ShapeNet. Thus, SCARP reduces the need to capture the object from multiple views or store additional CAD or mesh or full point clouds for shape completion for improved grasping. We end our presentation with two examples of shape completion on real-world scans of objects in our lab taken using depth cameras. To the best of our knowledge, we are the first one to do shape completion on partial real-world scans. SCAR performs equally well on these objects, indicating the benefits of our model. To summarize, SCARP learns rotationally equivariant pose features and geometric shape features to shape complete objects in arbitrary poses. SCARP is trained using a multitask objective that performs canonicalization, 60 pose estimation, and shape completion in a single network. SCARP outperforms existing baselines by 45% on shape completion metrics and reduces incorrect transposes by 70%. Thank you for listening to us.